Today, I am presenting on career pathways and skills required in quantum computing. Instead of explaining the complex physics behind how quantum computers work, I will focus on how students can enter this field. Many people are curious about what degree they need, whether a PhD is required, and what skills employers are looking for. My goal is to make this topic understandable for non-experts and help students see possible pathways into this growing industry. This presentation explains how computer science, physics, mathematics, and engineering connect to quantum computing careers, and what steps students can take to prepare. Before we dive deeper, I'll briefly outline the main topics I will cover today. In this presentation, I will first explain how different academic fields connect to quantum computing careers. Then I will answer common questions about what degree you need and whether a PhD is required. After that, I will discuss important programming languages and technical skills. Finally, I will explain why this topic matters and how students can get started right now. This slide shows an example of a quantum processor. Companies such as IBM are investing heavily in building quantum hardware. While the machines themselves are highly technical, what is important to understand is that teams of programmers, engineers, physicists, and mathematicians work together to make this technology possible. This highlights how collaborative the field truly is. Quantum computing is interdisciplinary, which means it combines multiple areas of study. Physics provides the foundation of quantum mechanics, mathematics supports the field through linear algebra, probability, and complex numbers. Computer science focuses on algorithms, programming, and software development. Engineering builds and maintains the hardware systems. You do not need to be an expert in all of these areas immediately, but understanding how they connect helps students choose a starting point based on their strengths and interests. One of the most common questions is what degree is required to work in quantum computing? The most common majors include physics, computer science, mathematics, and electrical engineering. Physics is often associated with quantum theory, but computer science plays a major role in algorithm design and programming. Mathematics supports the theoretical structure of the field, and engineering is critical for hardware development. Another important question is whether a PhD is necessary. Based on industry trends and education research, a large percentage of professionals in quantum computing hold a PhD, especially those in research positions. However, not all roles require one. Many software development, systems engineering, and applied quantum roles can be obtained with a bachelor's or master's degree. The key takeaway is that while advanced research often requires a PhD, there are multiple educational pathways into the field. Programming is one of the most important skills in quantum computing careers. Python is widely used in the industry. For example, IBM developed Qiskit, which is based on Python. Microsoft created QHash, a programming language designed specifically for quantum applications. In addition to programming languages, students need strong foundations in linear algebra, algorithms, and problem solving. Analytical thinking is extremely important. Collaboration and communication skills also matter because quantum computing projects often involve teams of physicists, engineers, and software developers working together. I have given two links, one for IBM Qiskit and one for Microsoft QHash, and these are two outside resources that you can use to see how these programming languages work. Quantum computing is a rapidly developing industry with growing investment from technology companies and governments. Universities are adapting their programs to meet industry demand, and research shows that there is still a skills gap between education and workforce needs. Understanding career pathways helps students make informed decisions about which classes to take, which internships to pursue, and whether graduate school is necessary for their goals. Preparing early can give students a competitive advantage in this emerging field. By understanding how education connects to industry demand, students can better plan their academic and professional future. If you're interested in quantum computing, there are practical steps you can take right now. First, take courses in linear algebra and programming, especially Python. Second, explore beginner resources from IBM Quantum and Microsoft Azure Quantum. These platforms allow students to experiment with quantum programming tools online. You can also watch introductory career videos, read discussions on forums, and try quantum simulators. Gaining research experience or internships in related areas such as software development, cybersecurity, or electrical engineering can also help build relevant skills. Students should focus on building strong foundations in math and programming while exploring interdisciplinary opportunities as next steps. In conclusion, quantum computing careers are built from multiple disciplines, including physics, computer science, and mathematics and engineering. While many professionals in research positions hold PhDs, not all careers in this field require one. Programming, analytical thinking, and strong mathematical foundations are essential skills. The field is regrowing, and students who begin developing these skills now can position themselves for future opportunities. Quantum computing is not limited to one major or one pathway. It is a collaborative and evolving field that welcomes diverse academic backgrounds.